Anyway, this is going to give us an idea on 6 degrees of freedom, 3 linear motions at the top, 3 rotary motions about 3 different axes at the bottom. And of course, same information pertaining to the 6 degrees of freedom have been shown in the other set of slides. And this is the slide what is going to give us an idea on the number of degrees of freedom that was associated with our human hand. 22 degrees of freedom have been attached. We are finding it difficult to accommodate 3 to 6 degrees of freedom for the entire robot together, whereas for the human arm, rather for the human hand alone, there are 22 degrees of freedom. So what is this degrees of freedom of a rigid body is defined as the number of independent movement it has in space. Flexibility of a robot increases with an increase in the number of degrees of freedom. For each degrees of freedom, one joint is essentially required. The degrees of freedom of robotic system can be compared to the way in which the human body moves. Degrees of freedom located in the arm defines the configuration. 3 degrees of freedom that are located at the wrist gives flexibility to the gripper or end effector. 6 degrees of freedom are required to locate robot's hand at any point in its workspace. Maybe I might be trying to use the same sketches whatever I've used earlier, but still it is meaningful to show this particular image showing 6 degrees of freedom. See, like first axis, second axis, third axis, fourth axis, fifth axis, and sixth axis. So it is essentially required in order to maintain complex movements. That too, when you want to lift and deftly manipulate the heavy payloads, and when you want to move them precisely, associated with complex geometries, definitely 6 degrees of freedom are required. And again, 6 degrees of freedom, out of them 3 translatory motions and 3 rotary motions. And those motions, when it was asked to show it on a robot, this is how they are: vertical traverse, rotational traverse, radial traverse, pitch, yaw, and roll. All the 6 degrees of freedom have been shown in this particular image. So though the information has been repeatedly shown, it was actually to give you a recall. And if you have not understood with reference to one, and you will at least be in a position to understand the other. Keeping that particular aspect in mind, these traverses have been showed again. Okay, so let me stop at this point. Thank you. I will continue my session with now under this we are going to cover, or we'll have discussions on robo configurations. So this image we have already seen, wherein you have got base being attached to the ground, link 0, 1, 2, or maybe 1, 2, 3, end of arm. At that location, the wrist is going to be attached. Industrial robots are available in a wide variety of sizes, shapes, and physical configurations. Majority of today's commercial available robots possesses one of the 4 or 5 basic configurations. They are as follows: polar configuration, cylindrical configuration, Cartesian coordinate configuration, jointed arm configurations. These are the major categorizations under configurations. We'll see simple sketches pertaining to them. And there is fifth one which was not showed over there is Squara, that is an extension to one among them. See, polar, that resembles a workspace. Maybe if you try to consider the end effector being attached to this, that end effector can be moved in a space wherein you can move that in a spherical environment. Then cylindrical, you'll be able to use, maybe you are going to attach your end effector to this with the support of the wrist. You'll be able to achieve the movements, something, maybe you'll be able to move the end effector in a cylindrical working environment. That you can see here. You can move this up and down. You can move this forward and backward. You can rotate this. Something exactly an environment similar to the cylinder. Coming to this Cartesian, see, you have got three linear movements. You can imagine what type of joints can be used for this. Vertically upward, maybe to and fro, and of course even maybe if you refer to this as some direction, maybe something like y. If you assume this as x direction, this is going to be the direction for z. Okay, so this is for z, this is for x, this is for y. Now coming to the jointed arm, you can see the flexibility and similarity. If you rotate this one by 90 degrees in clockwise, then it exactly resembles your human hand. See, shoulder joint is actually this. Then you have got arm here, one arm here and another arm here. So exactly resembling your human arm. And of course, this one, if you try to refer, there is some difference between jointed arm. There is one extension over here. Even this is actually extension. Okay, you're going to get some kind of flexibility over there. So polar configuration, the figure whatever has been showed here on the signal rounds. Maybe the right side sketch, whatever has been showed there, is trying to give you the information. Maybe you can, maybe at this particular joint, you can permit that to rotate by beta, and the base about this axis can be rotated by an angle called theta. And if you want, you can extend and retract. Okay, so you can increase the radial distance, something similar to the spherical configuration. Same information, three motions that are all pertaining to the body and arm together have been shown. Same thing again. Okay. So it is trying to use the telescopic arm. See, this radial has been written over here. That is actually something like it can come forward and backward. That is being referred as telescopic arm that can be raised or lowered. Okay, about a horizontal pivot. The pivot is mounted on a rotating base. It uses one prismatic joint and two revolute joints. These joints provide the robot with the capability to move its arm within a spherical space. Hence, it is called a spherical coordinate robot. This uses one twist joint and one or two rotary joints and or one linear joint. So we have seen in the earlier discussions that what is T and R and L. So in order to achieve this polar configuration, you can go ahead with either with TLR, TRL support or TRR type. Okay, these are the examples, and this is the sketch what I've tried to use at the time of history being discussed. So huge thing it is. It was not bothered about the shape. So there are certain advantages. Their vertical structure conserves floor space. Their deep horizontal reach is useful for far-reaching operations. Their capacity is capable of carrying large payloads. There are certain disadvantages. Their overall mechanical rigidity is lower than that of the rectilinear robots because of their rotary axis must overcome inertia. Okay. Their repeatability and accuracy are also lower in the direction of rotary motion. Their configuration requires a more sophisticated control system than the rectangular robots. If you look at the applications, if you look at the applications,